Start recording. Put it on the side. Okay. So I think we're good to go. All right. So we copy the algorithm and put it into the spreadsheet. And then we'll start another trace sheet. Line number. And the first line outside of the definition of a subroutine is 25 here. So other than the precondition, on line 25 we have our first invocation of main. So we got return info of post. Okay. Oh, right, we need comments here too. So, thank you. Get rid of that. And over here, now we have return info, which is just post, because there's nothing after the invocation of main. When we allocate for local variables in main, we have only one local variable, which is b, but b is an array, and we need one column per element in this case. So we need to allocate 4 columns for the entire array. So there are 2 ways to represent it. You can say B, and then you just say, element 0, element 1, element 2, and element 3. So that's one way to do it. I personally kind of like it this way, because now when we refer to B, we know that B is referring to all 4 columns. B is referring to columns D, E, F, and G. It's just that when you say B bracket 0, then we are talking about just column D. So I personally kind of like this representation, but in the test, you can use this notation. Oh, you're just double checking? Okay, well, it's working. Thanks. All right, but because B as a whole is a local variable, so it has unknown values. But it's not just one single question mark, because every single column is representing a individual value, so each one is unknown. So we need 4 question marks in this case. So one single question mark is not going to be the correct answer. We need 4 question marks, 1 for each column. Okay? And that's all we need to set up in main. So now we continue execution in main, which is just starting on line 19. That's the initialization of stuff. So we have 7, 2, 14, and -6 on line 19, 20, 21, and 22. This time I counted correctly. On line 23, we call the subroutine. So in this case, on line 23, it looks kind of funny because it is a print statement, except a part of what I'm printing depends on the value, the return value of invoking the subroutine find max. Okay, well, we just say that I don't know what I'm supposed to print until the invocation is done. That's the bottom line. So we have to invoke the subroutine find max first. When that invocation returns, then I know what to print, right before the quoted string is the index of the largest element. Okay. So that means at this point I have to invoke the subroutine called find max, and I need to set up the columns accordingly. So return info in this case is going to say, yeah, we got to come back to line 23 when we are done. What do we do when we come back? We still have to print. Whatever the return value of this invocation is going to be the question mark. And then we are going to concatenate the rest of the string to it. And of course, I cannot remember exactly what the string was. So the string is the index of the max value. So I'm going to specify that here. Is the index of the max value, okay, which is really just a waste of space. So I'm going to wrap it around here because I don't want it to take up too much space. There we go. And it has 2 arguments. It needs 2 arguments. When you look at the subroutine, find max, it needs one single parameter. which is parameter A, it is an array of integers. So that's going to take up another column. And then the local variables will take up additional columns as well. So we have one column for I, one column for M. The parameters, in this case, they are just integers. So each one is only going to take up one column, and they start with unknown values. A is going to be the slightly more complicated one, because for one, it is passed by reference, and two, we're passing the entire array B by reference to A. So now we have to say parameter A is a reference to a bunch of columns. And the columns range from column D to column G in this case. Do we have any questions about how we set up parameter A? Is that good? Okay, all right. So we'll adjust the width of these columns just a little bit. There we go. And now we can continue execution in the subroutine. So in the subroutine, we start with line 6. On line 6, M gets initialized to 0 because we make the assumption that the first element is the largest because we haven't seen the rest yet. On line 7, we initialize I to 1 because I controls which element in the array am I going to examine next. And then we get into the loop on line 8. Line 8 has to evaluate the condition, so we have to indicate, is I less than bar A bar? Well, I is 1, bar A bar is 4, 1 is less than 4 is true. So we go into the loop, we go to line 9, which has a second condition to evaluate. A bracket I is greater than A bracket M. So now we have to say, okay, what is I? I has a value of 1. Uh-oh, the other one is, okay, I need to move the window a little bit closer there. Okay, so I has a value of 1, so A bracket I is referring to A bracket 1. But when you look up A is not an array by itself. It is a reference to an array. So we are looking at the second element of the array that A is referring to, because I is 1, which refers to the second element. So the second element of the array that A is referring to has a value of 2. So that's A bracket I. What about A bracket M? M is 0. So we are referring to the first element of the array that A is referring to. The array that A is referring to is B, and the first element is column D. It has a value of 7. So the question is 2 greater than 7? Nope. Okay, so we say it is false. And so we have nothing to do in the conditional statement because the condition is false. We get to line 12, we add 1 to I. So I goes from 1 to 2. Then we get back to the beginning of the while loop on line 8. And we ask the same question again. Is I less than bar A bar? Yep, it's still true. Then we get to line 9. And we ask, is A bracket I greater than A bracket M? Well, let's check. A bracket I is referring to A bracket 2 because I has a value of 2, which is the third element of the array has a value of 14. Is 14 greater than 7? Yes. Okay. So we say the answer is yes, it's true. Then we get to line 10 because it is true. So now we update M with the value of I. So M becomes 2. Then we get out of the conditional statement, get to line 12. I is now incremented. So I goes from 2 to 3. Then we get back to the beginning of the while loop on line 8. I is now 3. We compare that to bar A bar, which is 4. 3 is less than 4 is true. Then we get to line 9. We compare A bracket I, which is A bracket 3, to A bracket M, which is A bracket 2. So we are comparing the last element of the array referred to by A to the second last element, to the second last element. So we are now comparing -6 to 14. Is -6 greater than 14? Nope. Okay, so the greater than condition is false, which means we have nothing to do because the conditional statement only has a then branch. So we get to line 12. Line 12 is adding 1 to I. So I is going to increase from 3 to 4. Then we get back to the beginning of the loop and reevaluate, is I less than, is I less than bar A bar? The answer is false because they're both 4. 4 is not less than 4. So we get out of the loop, we get to line 14. Line 14 just says return M, whatever M is, that's my return value. So we look up M, M has a value of 2 because that's the last time we updated, it had a value of 2. So we are returning 2. When we execute return and knowing what the return value is, all we are going to do is to copy and paste the return info cell, the rightmost return info cell, and then we change the question mark to the value that we are returning, which in this case is 2. Are we printing anything at this point? No. We are not printing, we are not executing line 23, we are executing line 14, which involves changing what we have to do on line 23 when we get back. But we are not back to line 23 yet. So now we move on to line 15. Line 15 is the end of the subroutine find max. So we got 2 things to do. One is to take note of where we need to go back to and what else we have to do when we get back. So that's just copying the entire return info cell. And then the second thing we have to do is to look at everything that we have allocated for this invocation. And then we say, none of that is needed anymore because we are done with this invocation. So we indicate that these columns are now deallocated. And now we continue execution on line 23. So in what it's going to print is just 2 is the index of the max value. That's what it's going to print. So nothing too exciting when we get back. And then after that, we get to line 24, which is the end of the main subroutine. And that's pretty easy too, because all it has to do is to take note of where to go back to, which is this post. So we basically say we're going to go back to post, and then we have no use of the columns that we had allocated for this invocation. So all 5 columns are going to be deallocated here, which is on line 24. So we indicate that these columns are now deallocated, like so. Then we continue execution at post, which means we're all done. So the end result of this entire algorithm is really just this. It prints 2 is the index of the max value to the screen. That's the actual effect of the program. Do we have any questions about this one? No questions? Yep, go ahead.
For this particular program, is there a reason why we wouldn't want to actually print the value to say what the value is as opposed to just what the index is?
Not in particular.
Would that change much with the actual code itself to represent the value?
Oh yeah. Can someone tell me what you need to change in the algorithm so that it prints the value of the array element that has the largest value? It's a very minor change. So the invoke find max b specifies a is going to give us the index, right? So all we need to do is to utilize the index in a square bracket. So if you're interested in not the index but the value, then all you're going to do, or all you have to do, is to specify the bracket notation around the invocation. Yeah, because your invocation of findMax is giving you the index of the largest element of the array. And if you want to print the value of that element instead of the index of the element, then you just utilize the index and go like, oh, we'll stick the square bracket around it so that we are now getting the value of that element instead of just printing the index of the element. So is that answering your question? Isn't that kind of cool? You can stick an invoke to any place. If it returns an integer and that integer is guaranteed to be within the range of all the indexes in an array, you can put it inside the square bracket. It's fine, not a problem. Same mechanism that we have talked about so far. Because the return statement doesn't really care how you are going to utilize the return value. All it says is, okay, you asked me something, here's the answer. Do whatever you want with it. Is that okay?
That's funny.
But it's used a lot. I mean, so this kind of, I will address your question next. So this really kind of differentiates between an experienced programmer versus a beginning programmer. A beginning programmer will typically use an assignment statement before this, and it will put the index of the maximum element into a variable first, and then in the second statement would use the variable to access the value of the largest element in the array. Whereas a more experienced programmer is going to go like, oh, we don't need an intermediate variable, just stick the result of the invocation directly inside the square brackets. Yep, go ahead.
Could you just return the value of the element instead of changing?
You could, but if you return the value of the largest element instead of the index of the largest element, then you can no longer get back to the index. If you return the index, it can always get back to the value. But if you return the value, then you cannot go back to the index. There are situations where the index is actually useful. For instance, if you want to implement bubble sort, not bubble sort, insertion sort, okay, then returning the index is going to be helpful. You guys know what is insertion sort or selection sort?
Where you want to add a value into an array?
No, it's about exchanging. Okay, so I can give you an example. I'm not going to present the algorithm. I can present the algorithm, but tracing is going to be so tedious that we don't want to do it.
What's the general idea of an insertion sort?
Insertion sort is actually not what I want to talk about. It's actually selection sort. Okay, so we'll go ahead and just play with selection sort. Actually, the best way to do it is using a spreadsheet because it's already a table. So I don't have to use a text editor to pretend to be a table. So let me pick up, this one will work. So I'll give you an example by hand first, and then you guys can help me maybe use the rest of the time to derive the algorithm, which is actually a part of the class that, a part of the important part of this class. So I'll just go ahead and use some random values here. So we'll have 5, -2, 0, 7, 11, and let's say 3. Okay. So I'm not even looking at this as an array. I'm just saying that, well, this is a bunch of numbers and I want to sort it in a non-decreasing fashion. Okay? So if I ask you to say, okay, give me the sorted version of these numbers, I mean, most of you can probably just eyeball this and go like, oh, okay, it's going to be -2, 0, 3, 5, 7, and 11. Okay? It's not that big of a problem. But if I want you to write an algorithm to do it, well, that's a different story, right? So the way selection sort works is it finds out what is supposed to go to column A first. Okay? So the way it works is it will look through everything here, and it goes like, okay, who should really be using column A? So you find the smallest element first. So you go like 5, okay, assuming 5 is the minimum. Remember find max? This time we're doing find min, okay, finding the minimum. So we say, okay, assuming 5 is the minimum, let's see. Oh, okay, -2 is less than 5, so this is actually the smallest one so far. 0 is not less than -2, 7 is not less than -2, 11 is not less than -2, 3 is not less than -2. Ah, okay, so this is supposed to be going into the first column. But then what happens to the thing that was in the first column? You swap them, okay? So now you exchange the value of what should go into the first column with whatever was taking the first column. So you exchange those two. The rest stays exactly the same. Okay, don't touch the rest. So you just have the rest being exactly the same as before. So now you look at the second row and you say, okay, I know the first element is already in place because I found the smallest one and stick it into the first place. So now when you scan from the second item on. And you ask, other than the first element, okay, which one is the smallest now? You go like 5, assuming 5 is the smallest one. 0 is less than 5. 7 is not less than 0. 11 is not less than 0. 3 is not less than 0. So the second smallest item is 0. Or from the perspective of column B to column F, 0 is the smallest. Let's make sure that 0 can get to the first place, right? So what about the thing that was in the first place within this portion? Exchange them, okay? So you exchange the 0 and the 5, keep the -2 the same way where it was, and keep the same place with the rest of the array. Is that okay? So at this point, by the time I'm done with row 3, the first 2 elements will be in place already. They're fine, okay? So now we start with the third element. We go like, okay, assuming 5 is smallest. 7 is not less than 5, cool. 11 is not less than 5, cool. 3 is less than 5. So 3 is supposed to go to column C. So what about the thing that is already in column C? Exchange them. So now we say 3, you're supposed to go here, and 5, you're not supposed to be there. Let's stick you to where 3 was. So we exchange those two. The rest stay put, okay? So -2 is still here, 0 is still here, 7 is still here, 11 is still here. So on row 4, we now make sure that the first 3 elements are in place, okay? So now what is left to do is to look at column D, E, and F and ask, okay, assuming 7 is the smallest, 11 is not less than 7, 5 is less than 7. So 5 and 7 should exchange. So now we stick the 5 here and 7 over here. 11, you stay in place, and then these 3 also stay in place. So now we have the first 4 elements already sorted, and now it's just down to these 2. So assuming 11 is the smallest, we just find there's something less than 11, which is 7. So 7, you go here, and then 11, you go where 7 was. And we're done. There's no need to go any further because when you have sorted the second last item, the very last item has to be in the right place already. Okay? So now we have sorted the array. So this is called selection sort because for each row, what we are doing is selecting the thing that should be at a particular place. And then we exchange the thing that should be in that place with whatever was in that place originally. And then we move and say, okay, the first part of the array plus this element is now done, and then we just process the rest of the array. So you can see how this particular algorithm can make use of a find min function that returns not the minimum value, but the index of the minimum value, because we need that in order to perform the exchange operation. Is that okay? So does anyone want to look at the selection sort algorithm?
Bubble sort.
This is selection sort, not bubble sort. You want to know what bubble sort does? Bubble sort is also interesting, so I'll tell you what bubble sort does. So let me comment this first. So this is selection sort. Bubble sort is a little bit different. So we'll talk about bubble sort here. Bubble sort. Okay. So what bubble sort does is it will exchange when things are out of order. Okay? It will only compare an element to the neighboring element. If they seem out of place, exchange. And then move on, compare. If they seem out of place, exchange. And so on and so forth. Okay? So what it will do is it's going to look at 5 and -2. Are these 2 out of place? I want the array to be in a non-decreasing order. They are out of place. Okay? Exchange them. So now you have negative 2 and 5. So now we compare the 5 and the 0. Okay, so if I really want this to be step by step, it's going to be quite tedious, but it's okay. All right. So now we look at these two. Are they out of place? Yeah, they're out of place. So we got negative 2, exchange only these two, leaving the rest the same. So now we look at these two. Are they out of place? Nope, they're in place. Look at these two. Are they out of place? Nope. Are these out of place? Yep. Okay, well, exchange them if they're out of place. So now this is the state of the array. Then what do we do next? Yep.
Would you be able to just use like another while loop to
Yep.
go back through the process?
Yep.
and check it?
Yep. So then what we do now is to do it again. Okay, so it's called bubble sort because we are bubbling things up. That's why it's called bubble sort, okay? Because in each, so if we call this one big iteration, then in each big iteration, things will move up by one position. If you imagine that negative 2 was originally here, it would now be here, and then it would be here, and then it would be here. So you can see things quote unquote bubbling up using the bubble sort. But we can do this, okay? So in the next iteration, we look at these two and go like, are they in place? Yep, they're in place. Okay, so we'll, okay, I'll just kind of keep these the same. So the first two are in place. Is the 0 and the 5 in place? Yes. Is the 5 and the 7 in place? Yes. Is the 7 and the 3 in place? Nope. Exchange those two. So the rest is just going to be copied and pasted. And then in the next iteration, we compare the 7 and the 11. Are they in place? Yes. Okay, so we are done with that round through the entire array. Then we do the same thing again. Negative 2 and 0 in place. 0 and 5 in place. 5 and 3 not in place. Exchange those two. The rest stay the same. Right there. And then we do it again from the very beginning. Negative 2 and 0 in place. 0 and 3 in place. 3 and 5 in place. 5 and 7 in place. 7 and 11 in place. So when everything is in place, then we can exit. Yep.
Is this one of the instances where you would want to use like a post-conditional statement, like a repeat until?
Yes, because the repeat until, because you need to scan through it at least once to see whether the whole thing is already in place. So that is correct. So this is in, but you have to indicate whether you're dealing with the inner loop or the outer loop. Because it is a double loop, there's one loop inside another loop. So that's bubble sort. So bubble sort, selection sort, as it turns out, it doesn't really matter you pick. They both suck. They both suck because they have a time complexity of n squared, where n is referring to the size of the array. What does that mean? Time complexity is n squared, or the size of the array squared. That means if you double the size of the array, the amount of time it takes to sort the array is quadrupled. If you triple the size of the array, then the amount of time is going to be 9x the amount of time originally. If you quadruple the size of the array, it would take 16 times the original time. Yep. So that's what it means when we say the time complexity is the square of the size of the problem. Okay, and they both are like that, okay? So, bubble sort and selection sort, they both have the time complexity of the size of the array squared. Then you go like, well, in that case, are there any better algorithms that can do sorting? Well, as it turns out, there's a whole bunch of sorting algorithms that can do better than n squared. They're called n log n. So you multiply n by the log of n, and that becomes the time complexity. So how much better are we talking about? You have to plot the curve, okay? So look at the curve where you have n squared. which is going to look like a parabola or half a parabola. It's going to look like this. And then you look at the curve of n log n, which is still not going to be linear, but it's going to grow a lot slower. So we are looking for algorithms that are faster. Merge sort is one of those things. Okay, so we'll look at merge sort. So merge sort is interesting.
I think there's a whole website that actually goes through like sorting algorithms.
Oh yeah, if you go to Wiki.
That they're sorting by lane, and there's like hundreds of them that you just watch. It's kind of satisfying.
They'll make someone's Christmas light.
Actually, that'd be super cool to do just lights like that.
You just hang, numerical display, around the entire house, and then you just run different sorting algorithms. So those numbers, it's like that.
Or do it on like a garage.
Yeah.
All the lights, like,
Oh, if you want to do on a garage door, it's easy because you can use a projector.
Dude, that might be nice. That would be so cool.
I've actually listened to sorting algorithms before, like instead of like watching them, I'll listen to them, and sometimes they actually sound musical. They're at least very satisfying to listen to.
They're all over YouTube. You can find so
Yeah.
many different kinds of them.
There is a European dance to explain sorting algorithms. You gotta watch that. If any one of you is into, folk dance, okay, I gotta show you that one. Yeah, this one, I cannot ignore this one. So it's sorting, dance, video. There's a whole bunch. It's funny. Bubble sort, Hungarian dance. Okay, there we go. So they got bubble sort, they got merge sort. Okay, gotta watch it, right? I mean, now that we are here, why not? And this is not inappropriate.
Yes! This is what I'm talking about. It's these things. They're so cool.
No, but I want to watch the dance.
What happened to the dance?
No. No, this is the wrong video. I clicked on something. I clicked on the next video, I think, by accident. There we go. Okay, there we go. Okay, I got to turn off the light because you can't see the numbers otherwise. It's only displaying one part of my screen, that's why. Even array notations. So these two are out of order, so they have to exchange. So 3 and 8 are out of order. Oh no, 3 and 8 are in order, so they don't swap. And then 7 and 8 are out of order. 2 and 8 will have to swap too. And 8 and 5 are out of order. They have to change. Okay, what? Yes. So bubble sort is interesting in the sense that it only has to compare neighboring neighboring elements of an array. But you can actually see, it takes a long time to watch the entire thing, but it gives you time to process what they're doing. So 0 and 1, there's no exchange. 1 and 3, no exchange. 3 and 7, no exchange. And then 7 and 2, those two will have to exchange. See?
Oh, you got some homes, huh?
Now, of course,
You can speed this up like this.
this is very nice as a relaxing kind of mechanism.
How about you slow it down and remove half the frequencies? No, put a blue and pink filter with like scan lines.
Why don't they do bubble sort, like, because they go all the way to the right and then they start over from the left? Why don't
Yes.
they go all the way to the right and then back to the left and keep going?
Well, they don't have to go all the way because, you can see the people who have turned their back, those are done already.
Oh, okay.
So they are not even being compared. So this time they will only compare up to these two guys, up to this guy, because the ones who have turned their back means they're already in place. They are already at the right place. There's no need to compare those anymore.
It's not intuitive.
So to be culturally, correct, now we need to make, the same kind of video, but with different types of culture, different kind of dance, right?
Well, it seems like they do different cultures all dance.
So my question remains the same. Why don't they sort in a kind of like ping pong manner instead of starting at 0 every single time?
I think selection sort is going to do that. So if you guys are interested in, this sort of thing, so they're done now. Yep. So there's a little conclusion, right? Yep. Now, in the days of CGI, we can actually do all of this without actually people, right? Yeah, we just have to.
I'm gonna do it with Pixar animated.
Yeah, we can make a new Pixar movie. Just call it Sort, right?
Yeah, it doesn't have to be like just one word, right?
Teach kids how to program.
Yep, exactly. Yeah. So you got this, and then you got quick sort, merge sort, insert sort, select sort, binary search. Oh, this one is Flamingo. Sorry? Huh? Flamingo? Oh, Flamingo is good because this is also binary search, which we talked about. So let's take a look. So the array has to be sorted, right? And it has 7 elements, which is a power of 2 minus 1. So 7 is the value that we are looking for. It is going to go to the one in the middle and compare first. Who's my match? Hey, this is supposed to be what? Binary search. So he's looking for the one in the middle, compare. Of course, without the music, it's not the same. Come on, what's her number? Worse than watching the Dragon Ball. Oh, 7 and 5, okay. So those cannot match. So they all turn their back. So now we have to find the middle of the remaining 3. Or Naruto, for that matter. Let's have a flashback. Another flashback of a flashback. Naruto is best for explaining recursion because we have a flashback of a flashback of a flashback. Okay, so 7 is less than 8, so those 2 cannot be the value. Now you have only one element left to compare. same. There you go. All right.
It's not nearly as popular.
I liked it.
It's too slow.
Also, it's like 15 videos down.
Hmm?
I learned that I like
Way down in on the relevance.
I want to watch MC Hammer doing this. I want to see MC Hammer finding his match, yeah, hammer time, right? So he'll call it binary time. Okay, I'm gonna turn the lights on. So close your eyes. There you go. Okay. So yes, so there are lots of demonstration of these sorting and searching algorithms that you can actually look online. They explain the mechanism, but they don't tell you how to write the algorithm. They show you how it works, but how do you find out, okay, now that I know how it works, how do I write the algorithm? Okay? Google, yep. Well, that's a very good answer, okay? That is a very good answer because the first thing you do if you are working in the field is you Google. So you Google and you look for sorting algorithms.
I have a teacher that calls it Google Kung Fu.
It's
What?
not how much you know at a job, it's how quickly you can look it up.
Well, and also do you know how to interpret what you're seeing, okay? Because Wikipedia is great if you spend the time to understand what the article is about and click on the links where you say, okay, I have no idea what a permutation is. So instead of just going like, I sort of know what a permutation is, I'm just going to continue on with this article. You have to right click on permutation, start a new tab, and then read what a permutation is. Once you understand what a permutation is, then you go back to this article and continue with this article. So it is not uncommon that I have like 20 tabs open to look into one particular thing because I just look it up and go like, okay, I don't understand that term either. Click on that, and it explains it in terms that I don't understand. Click on that. So I go through a particular search algorithm to look through all of that stuff to understand the concept. So, okay, so now that we are on the search algorithm thing, it has efficient sort, it has bubble sort and variance, distribution sort. So when you look at the efficient sort, like Mergesort, it tells you a big O notation. Okay, I know it's kind of small, but it does give you a big O notation. And I was just talking about the big O notation today with my cisp300 class, which is basically the last class you're going to take in the computer science or the computer science transfer program. So the big O notation is basically a way to say how fast is the amount of time it takes for the algorithm going to grow with respect to the size of the problem. This is n log n, which is better than n squared. In fact, when you move on to a 4-year university, there's an upper division class called Analysis of Algorithm that says you cannot find a more efficient algorithm than big O of n log n. So the moment you find that your algorithm has a time complexity of big O n log n, you're done. Cannot be any better. Isn't that interesting? You can mathematically prove that there exists no algorithm that can be faster than anything that already has an n log n time complexity. Yep.
Didn't the guy that came up with the algorithm before big O and log n say the same thing?
What same thing?
That his is the fastest that you could possibly get until someone discovered another algorithm that was faster.
I don't think so, because it is mathematically provable that there exists no algorithm faster than n log n time. Now there can be ties, okay? So merge sort ties with heap sort ties with a whole bunch of other sorting algorithms, but they all have a time complexity of n log n. Yep.
So if you're trying to create algorithms, how would you prove that your algorithm has the complexity of big O and log n?
That is what you learn in the upper division class at a 4-year university. It is called the Analysis of Algorithms.
So you go counting operations, number of operations.
It is a kind of tedious process because you start with the algorithm and then you analyze How many times do we go through this loop? How many times do we go through that loop? And so on. Yep.
If I don't want to wait for my 4-year university, do you have a website you recommend?
Google.
You can Google, because the analysis of algorithms, there has to be like plenty of videos even, on YouTube. Dancing may not be one of them.
Dancing to how to find.
Yeah, y is n log n fastest in sorting, okay? So generic and practical algorithms faster than big O of n log n. Well, this is this is Stack Overflow, which means people may ask kind of stupid questions. Is it possible to sort an array faster than n big O of n log n time? Okay, you can click on that.
Short answer, no.
And it refers to the book. So it says, possibly this question arises in the mind of every person who has once come across the subject of design and analysis of algorithm, which is very different from this class, which is supposedly the algorithm design and problem solving. Okay? Well, just because you can design an algorithm doesn't mean it's going to be efficient or even correct. Or even syntactically correct in this class because we're using pseudocode. Okay? So generally we assume that the best time possible to sort an n-element array is big O of n log n. And it turns out that this assumption can be proven mathematically as well. Okay, so the proof is, and turns out that this is not possible when we restrict ourselves to sorting algorithms that are based on comparing array elements. The lower bound, So you have to understand, all those terms. What is a lower bound? What is an upper bound? I know, we intuitively understand what is a lower bound, but mathematically there is a definition because I just went through that definition today, like 3 hours ago, with my cisp300 class. So there's a whole bunch of math and logic and analysis involved in the process of proving that n log n is the best time you can do with an array and a single-threaded processor. Because if you say, oh, but I have like 6 cores, okay, how do I utilize all 6 cores to perform a sorting? Then it becomes different because now you can have algorithms that cannot utilize multiple cores, that cannot benefit it, or you can have algorithms that can split the job into like 6 different things and they can all do computations at the same time. So there are assumptions that they are using when they use n log n, which is basically a single processor, single thread. Questions? Nope. All right. So are you guys looking forward to moving on to a 4-year university? Yep. Cool.
Kind of a way to get around n log n is more processors, more threads, more cores kind of thing.
Yes. So, potentially, yes, algorithms can be faster than n log n if you can assign multiple processors because you can do comparisons and exchanges at exactly the same time in that case. So in the case of Mergesort, so what they do is they split the array into 2 halves. It's like, okay, you process this half, you process that half concurrently. Okay? So when both of those are sorted, now you have to merge those 2, which is a pretty easy task to combine those 2. So that becomes better than n log n if you can assign an arbitrary number of processors to perform operations in parallel. So there are interesting assumptions that you can make when you analyze algorithms like that. All right. Any questions? So I think we still have that big question of after we watch all those Hungarian dance videos, we understand how it works. But how do we write an algorithm based on knowing by hand how it works? So what do you think? Where do you start? Yep.
You have to start by assigning like each value to an array element. Right?
Okay, so I would start with constructs, control flow constructs that we have learned, because there are only 3 of those in general in broad category. We got assignments, or sequences, which means you do one thing after another thing, but you cannot deviate, you cannot repeat doing something. We have conditional statements, which means we get to a point in the program, you can choose one of 2 paths, and then you execute one of those 2, and then they merge, and then you continue on. And then we have repetitions, basically loops, okay? So you have to look at the problem and go like, okay, does it seem like we are doing something repetitively? Most of the time, it is, okay? So you say, okay, we got a loop. So once you choose a loop, the next thing you have to evaluate, or the next thing you have to decide is, when do we get out of the loop? What is the condition to get out of the loop? So in the case of a sorting algorithm, is when you confirm that the entire array is sorted. I don't care how you can confirm that, but once you know it is sorted, you can get out. So you just write it down, okay? So now whatever you do in the loop has to do with getting closer to having the array sorted. So now you have to look into that. Now in the case of bubble sort and selection sort, they have a loop inside a loop, which means it's a perfect example to use subroutines. Because the loop inside the outer loop, it is better to abstract it into a subroutine and just go like, okay, this subroutine is only responsible for quote unquote 1 pass. So when you watch the Hungarian dance on bubble sort, you can see how the dance movement is always going from left to right, okay? So you define a pass is just one single pass of going from left to right. So you turn that into a subroutine, which makes it a smaller problem. So you look at the smaller problem and go like, okay, what is the smaller problem? Okay, the smaller problem involves starting from the leftmost dancer, comparing to the neighbor, and then keep going down until you hit a certain boundary. Okay, so you have to specify where to start is easy. It's always index 0. But where do you end? Well, you make it a parameter. So you keep comparing in place, if not in place, exchange, and then keep going. That becomes your subroutine. So once you have the 1 pass subroutine, then you go back to the main algorithm and go like, okay, so what does the first pass look like? We have to go all the way to the end. What does the second pass look like? We have to go from the first one to the second last item. What does the third pass look like? We have to go from the beginning to the 2 elements are already in place, so you don't have to go as far. So you basically go like, it begins with this much, then it becomes this much, this much, this much, this much, and then when there's only 2 left, then you're done. When there's only 1 left, then you're done. So that's kind of how you break a bigger problem down into smaller problems. We can talk about that on Wednesday. Specifically, we can look into selection sort and bubble sort, and then we can go through the process of converting what we observe into an algorithm. Would that be a good topic to go over on Wednesday? Okay. So I can try my best to formalize, or at least give you some steps of designing an algorithm. But a lot of that is really something that kind of pops up in my mind, and it's not easy to explain. But I can try my best to kind of explain, how I reason out the code of a particular algorithm. And the good thing is, I have a really bad memory, so I cannot remember the actual bubble sort algorithm, nor the selection sort algorithm. So I have to basically rework the entire algorithm from scratch because I don't remember it. So that's good. Just make sure that I don't read anything about selection sort nor bubble sort that I have nowhere to recall from, which means I have to derive the algorithm from scratch again, which means then I have a chance of explaining the process. Because if you ask a really good professor like Professor Entos, he probably remembers every single algorithm. So he cannot explain the process because to him it's just a recall. It's like, oh, I remember the algorithm, and he can write the entire algorithm from start to finish. I cannot do that. I have to reason everything back out, to put it into an algorithm. So we'll do that on Wednesday. Okay? I'll see you guys on Wednesday, and try to stay warm.